We could do the Panama version.
Good morning. My name's Bob Armstrong. I'm director of the MIT Energy Initiative, and it's a real pleasure to welcome you this morning to Solar Day at MIT. I'm joined up here at the dais this morning by Maria Zuber. She's a member of the National Science Board and Vice President of Research at MIT. She also holds the position as Griswold Professor of Geophysics in the Department of Earth, Atmospheric and Planetary Sciences. Professor Zuber has been involved in more than half a dozen NASA planetary missions aimed at mapping the Moon, Mars, Mercury, and several asteroids. She's currently the principal investigator for the Gravity Recovery and Interior Laboratory, the GRAIL mission, which is managed by NASA's JPL in Pasadena. I'm also joined by Professor Richard Smallensee. He's the Howard Johnson Professor of Management and Professor of Economics at MIT. He's former Dean of the Sloan School, and maybe more pertinent to this morning, he was chair of the Future of Solar Energy Study at MIT, which was completed last May. We're going to kick off the morning with some opening remarks from Professor Zuber. I'll turn it over to you, Maria.
Great. Okay.
Thank you.
Well, I'm delighted to be here this morning. Bob neglected to mention that I do study the sun also, but
You have no missions to the sun.
the gravity field of the sun. I got an idea for a mission to the sun. So, one of my favorite stars. So, there's a major challenge before us that many of the people in this room are working on solving. One that I hope many of the new students, some of whom are even here this early this morning, and I hope that you will take this on. By the middle of this century, the world will likely see a near doubling of energy demand relative to today. This is driven by growth in global population and increasing standard of living and the global GDP. At the same time, it's clear that in order to avert the worst impacts of global climate change, we need to rapidly reduce greenhouse gas emissions from the energy sector, notably CO2 emissions. Solar energy provides a tremendous opportunity to realize this low-carbon energy future. Some of you may have read, hope you have read, the Future of Solar Energy study authored by MIT faculty and researchers and released in May, which highlights the major advances in solar energy has made in recent years, as well as the challenges that it still faces. Today, we are going to get a glimpse into promising areas of solar research and technology development here at MIT, across all of our schools and departments that may help make the breakthroughs needed for solar energy to take its place as a major global energy source. The breadth of research in solar energy and in other forms of low-carbon energy is unparalleled in research universities around the world. This ability to work across so many disciplines is not only a characteristic of MIT, but is also a key in addressing the great coupled energy climate challenge. You'll see faculty from many departments sharing their work, hear from the students presenting their research in our afternoon poster session, and we are also very fortunate to have keynote speaker in Professor Ellen Williams, Director of ARPA-E, the U.S. Department of Energy's agency for advancing early-stage, high-potential, high-impact energy technologies. Today is also an opportunity for all of us to think about these challenges and how we can apply our collective talents to meeting them, putting the MIT motto of mens et manus into practice. The MIT Energy Initiative has been working on solar energy initiatives since its inception in 2006. Since then, MITI has generated more than $400 million in research funding for low-carbon energy technologies alone, the largest single technology focus of which is solar energy. Two of MIT's major roles in society are research and outreach. The Institute has long played the part of an honest broker and a convener of disparate groups of stakeholders in academia, industry, and government to bring innovation to the marketplace and to inform public policy. MITI exemplifies this role through its work with the many companies that sponsor faculty and students in low-carbon energy research. I encourage new students here today to take advantage of the many and diverse opportunities to contribute to solar energy research here at the Institute and to help play a role in realizing the solar future. Thank you very much.
Thank you very much, Maria. We're now going to shift to a discussion or presentation first and then questions and answers by Professor Schmalensee. As I said, he was the chair of the Future of Solar Energy study that was completed in May. That was the seventh in a series of future of studies that MIT's undertaken, looking at how we might meet this projected growth in energy demand that Maria referred to by mid-century in a carbon-constrained world. And as she also mentioned, solar is the big resource out there, and it's very timely to have this study completed this May. So with that, let me turn it over to Professor Schmalensee.
Thank you. Pleasure to be with you this morning. As Bob said, this is the latest in a long series, fairly long series of studies. It's important to get the question right. We assume that if we're going to limit the climate risk to acceptable levels, we'll have to decarbonize the electric generating sector pretty totally. It is also a reasonable assumption that this will be politically difficult unless it can be done at reasonable cost. You can see the difficulties that have surrounded carbon policy in the United States. There's a backlash in parts of Europe. Cost matters. So the question for solar is, can solar be scaled up to play a major role in meeting, say, mid-century energy demand? And that means a scale up by order of magnitude, a factor of 50, without blowing the lid off costs. Now, what makes this interesting, of course, and the question is, what policies would make this most likely? What makes this interesting, of course, is the scale and distribution of the solar resource. Just looking at the United States, you could generate in total all the electricity we consume on half the land we use to grow corn ethanol. And I won't talk about what a terrible policy corn ethanol is. Just by way of background, which I expect everybody knows, and you'll hear more about the two pathways to generate solar electricity: photovoltaics, a mature technology which really dominates the solar generation these days, which the output of which responds immediately, essentially, to changes in irradiation. Concentrated solar power, often called solar thermal, less mature, more expensive, needs clear skies, but is easily made dispatchable, and so quite interesting in that regard. Now, these are exciting times for solar. Capacity's grown by 40% a year globally since 2000. A little hint of what's going on is on the right-hand side. You'll notice that Massachusetts is on that chart as one of the states with a lot of solar. That's not because we have a lot of sun. I'll come back to that. But as I say, exciting times. Will it continue automatically? Is there any need for policy? Well, if you look at costs, first thing you note, it's small. Solar's about 1%. There's a lot of attention paid to the drop in the cost of the solar module. And it has been dramatic. But it looks like it has slowed. There's no Moore's Law here. There's no, and what matters is the cost of the whole system. You'll see a typical U.S. residential cost and a typical utility cost. They've gone down less. There's certainly no Moore's Law in putting brackets on rooftops or stringing wires or getting permits or generating leads for residential installations. Those costs have come down slowly. So the cost decline is not as dramatic as is often portrayed, and it's slowed. Moreover, the main reason Massachusetts was on that prior graph is we have pretty high incentives for solar. Federal subsidies are scheduled to be drastically cut from 2017. State programs have not expanded, and there has been a backlash against rooftop solar in some states. So continuing support is not automatic. So 2 more pieces of background. These are some cost numbers. They're always controversial. The main points they make is utility scale is becoming competitive without subsidy in some regions. You notice the big difference between California and Massachusetts. There's a tendency in discussions of solar to forget that it matters how much sunshine you have to what the costs are, much more expensive in Massachusetts. But residential scale is much more expensive, and CSP is much more expensive. And this is a simulation, but you see the point I'm about to make in the actual German data. Photovoltaic generation peaks at noon. If you have a lot of photovoltaic generation, the price received at noon is driven down. So the more solar generation there is, the lower the average solar owner price is in a market system. So that what's competitive at today's low penetration will not be competitive at high penetration. What that means is going forward, substantial cost reduction will be required for solar penetration to rise to high levels, for solar generation to play a major role in the mid-century energy system. So this is by way of background. I want to talk now about our 3 main messages for policy. First is R&D, and I'll do these in turn. We think federal solar R&D has been, to an important extent, misdirected, and we'll talk about how that should change. We think it's not, the system as it stands is not ready, technically or in regulatory terms, for high solar penetration, and it's time to start preparing for that. And finally, while we support continued subsidies, continued support for solar generation, the current system is sufficiently inefficient as to make the cost of high levels of penetration likely politically questionable. We don't get very much bang for the dollars we spend on solar generation. That can be fixed. Okay, let me talk about R&D. If you look at today's technologies, crystal and silicon, that's a technology that's been around for a long time. The private sector has a lot of incentive. There's competition, a lot of incentive to reduce costs. R&D, what the federal government is good at is long-term R&D, basic research. It's not good at wringing the last penny of cost out of an existing technology. So there's the cost system for utility scale and residential scale photovoltaics. Making in more detail the point I made earlier, costs are not dominated by module costs, they're dominated by everything else. Industry has the ability and the incentive to put pressure on those costs. They're lower in Germany for reasons that have to do with policy, but also have to do with experience and scale. The technology that's being deployed, crystal and silicon, is mature, it's efficient, reliable, and so forth. But the wafers are thick, they're rigid and heavy, and the manufacturing process is inherently complex. There are emerging thin film technologies that promise, by virtue of flexibility and lightweight, to lower total system cost. They are not ready for prime time. They are promising. A good deal more work is needed, but that's the sort of thing federal R&D is good at. Reducing the cost of brackets, not so much. Funding important breakthrough advances, perhaps. A word, and Bob would have me say more about concentrated solar power. Again, the costs are very high. Federal R&D, or the federal policy in this area, has been to subsidize commercial scale plants. Well, you don't seek fundamental advances when you put $1 billion into a commercial plant. What's needed isn't more subsidies for current technology. It's more focus on ways that you can reduce the cost by making advances in technology, by raising operating temperatures, more efficient collectors, higher temperature power cycles. And that's probably best done through demonstration plants, certainly not through commercial scale activities. As this points out, DOE has been going in the opposite direction. They have not focused much on fundamental technology. They've focused on getting costs down by 2020. And we think that won't do it, in short. So federal R&D, we think, should focus on transformative technologies, not near-term cost reductions, new and emerging thin film technologies, and in the CSP side, new materials, new system designs that permit higher temperature operation, and do that in pilot scale facilities. Preparing for greater penetration of PV generation. PV will dominate for decades. There are grid integration issues, and there are retail pricing issues. The grid, this illustrates part of the grid integration issue. This is simulation in Texas with increase. The brown is, the top line rather, is the unchanged total demand. The brown is what has to be made up from the fossil fleet, and the yellow is solar contribution during a day. That's it's a 29-hour day. It's one of the long days. But the key thing to note is the top of the brown is the maximum that has to be gotten from the rest of the fleet. And you'll see that doesn't decline much with increased solar penetration after a while, because solar generation peaks earlier than load. You also see that as you have more solar penetration, you place an increased ramping burden on the rest of the system. Look at the 58% graph. You see the fossil fleet has to ramp up rather rapidly as the sun begins to go down. This can be done, but this is not by any means automatic and requires certain characteristics of the fossil fleet. You can't do this with baseload coal plants. Well, now it's stalled. Okay, there we go. This is taking, my favorite picture is taking a while to load. I assume that's what's happening. Well, imagine, oops, let me go back. Imagine a very interesting picture. What that may someday show is hourly solar radiation at Golden, Colorado, hour by hour in 2012. All these slides will be posted, so the fact that I'm going rather rapidly, you can refer back to them. This shows a great deal of variation, some of which is obviously predictable, seasonal, diurnal. Some isn't. Their storm systems come in. It is very difficult to imagine very high levels of solar penetration making sense without cheap, scalable storage. Pumped hydro is a terrific technology. It's limited in its applicability. That's limited sites, very hard to build any more of it. People have been working on bulk storage for a long time, but it's really hard to see how you do solar at very large scale without storage. That makes it makes research on storage to us a very high priority. Now let me come, if this will let me move, to subsidizing, to the need to change how retail rates are set. This is the net metering controversy, which raises blood pressure all around the country, and is relatively simple to explain, I think, although people fail to get it. If you look on the left, the retail price you pay for electricity has two basic components, and I at least see it on my bill. The first is the cost of electricity purchased or generated on the wholesale market, and the second is the cost of maintaining the wires, the investment in the wires. That's a fixed cost to a first approximation. If I, customer A, put solar on my roof and sell to the grid, two things happen. One, I get a higher price for my generation than the utility scale operation across town. So it's an extra subsidy, which may or may not be a good thing, but it's an extra subsidy. The other thing that happens is somebody else has to pay the cost of the wires. If I'm generating and I'm not paying my share of the cost of the wires because I'm not using, I'm selling or I'm using my own electricity, somebody else pays. That's not theology, that's arithmetic. As I say, it gets people very angry. And the problem is, you know, what, is it fair, is it not fair? You can make detailed arguments about how you should charge for the wires. And it's work going on here at MIT on how to do that in a fair way. But the fact is, this is perceived as an unfair system. Who has a solar rooftop? Is it poor people that have solar rooftops? Not so much. Is it apartment dwellers that do a lot of this? Not so much. So there is and studies have shown this, there's a clear income transfer from the poor to the wealthy. The poor have to pay the cost of the wires, the wealthy shed it to a first approximation. That is going to become increasingly dicey as we build more solar. There is political resistance to this in a number of states, fierce battles. Even there's been debate in Massachusetts about should there be more net metering allowed. We can't price retail electricity this way and have a lot of solar as a political matter. That needs to change. So we recommend that research be done on storage. This is not a controversial recommendation. We also believe that we need to fundamentally change how we set retail electricity rates. Let me move on to our third message, which is the way we support the deployment of solar generation needs to be changed. It is wasteful, which is not necessarily a bad thing, but if it's wasteful, then at high levels of penetration, it becomes very expensive. We believe there should continue to subsidize. There are a lot of good reasons. We can talk about them if you wish, but we're paying more per kilowatt hour of solar generation than we need to. That's the basic point. And if you want a lot of solar generation, you want to minimize that cost. We have a huge array of subsidies in this country at the federal level, at the state level, no two states are the same, and at the municipal level in many cities. No one has a clue how much we spend, but we spend a lot. They lay the foundation, all fine, we don't have a carbon tax. The main federal subsidies subsidize investment, accelerated depreciation, the investment tax credit. They are scheduled to be eliminated or to be cut, not a good idea, but these systems need to be changed. So let me talk about first the investment subsidies. If you think about it for a minute, investment-based subsidies, capital-based subsidies subsidize generation more where it's more expensive, right? It's more expensive to put a a megawatt of capacity on rooftops than it is at utility scale. So you get more subsidy per unit of capacity where capacity is more expensive. It's more expensive given capacity to generate, or you get less electricity per unit of capacity in Massachusetts than in California. So we get a higher subsidy per unit of electricity in Massachusetts than in California. So you see the amount of subsidy per megawatt hour differs by roughly a factor of 3 between utility scale in California and residential scale in Massachusetts. And you have to ask, to what question is that the right answer? It's very hard to conceive it. There are also ways, which I won't talk about because they give us all a headache, the way you can use the residential system to get extra subsidies. This understates the problem. The investment subsidies are remarkably inefficient. The state renewable portfolio standards do subsidize generation. They subsidize generation regardless of when it happens, which is somewhat less of a problem for solar than for wind, which of course subsidizes generation at night when you don't really need it to an important extent. But all these programs are different, and they have siting restrictions. So to satisfy the Minnesota, I think it's true for Minnesota, you have to generate in Minnesota. Is Minnesota a great place to generate electricity from the point of view of the nation? Or to generate solar electricity from the point of view of the nation? Not so much. These programs are uneven across states. They are, by and large, have siting restrictions that require you to put solar electricity and solar generators in what may not be appropriate sites. They are needlessly expensive from the point of view of the nation as a whole. So our recommendations for deployment policy, again, don't cut it. They should be about generation. If what you care about is substituting for fossil generation, you should subsidize solar generation, not solar investment. Tax credits, I didn't talk about it, but tax credits are a remarkably inefficient way to do this. The Germans actually just give you money for generation, which seems like an odd thing to do if you're interested in generation, but it is rather direct. State programs, because of the differences among states and the siting restrictions, raise national costs. And I will say that the Clean Power Plan, because it is state-based, is going to exacerbate these differences and raise national costs. So the main messages, as I said, have to do with changing R&D policy, preparing for high penetration, and reforming how we do deployment subsidies. Thank you.
Thank you very much, Dick. So what I'd like to do now, we have maybe 5 or 10 minutes for questions, and I'd like to open it up to the audience to see if there are questions out there on this. Yes?
A question for Dick. You mentioned the need for storage, especially with increased PV generation, but I didn't hear too much about your thoughts on batteries and large-scale use of battery storage. What are your thoughts on that?
Well, at the moment, it's not economic. We need at least a couple of breakthroughs to get there, and there's active research here and elsewhere, and there's reason for optimism. Of course, the fact that we've been working on batteries for a long time and aren't there yet is reason for pessimism, so we'll see how it plays out. Batteries seem like the natural medium, but there may be others. Thermal storage in CSP plants is promising in some regions, not all regions. So
what I'd like to encourage you, if you have questions, we have microphones in the aisles on either side that would be good to use so everybody can hear the questions. Could you step back to the mic if you would? Yeah.
Yes.
Thank you.
So I also have a question for Dr. Schmelzi. I'm sorry, I'm bad with pronunciation.
I'll answer to almost anything.
So my question was, Do you have you witnessed through the study the fact that solar power might be hindered right now by cheap gas, and people that argue that gas is a better first technology to reduce momentarily carbon emissions by replacing coal plants or oil plants? Have you witnessed like that kind of argument politically,
Well,
cutting
sure,
subsidies?
sure. It's not, I mean, that's, the cheap gas cuts two ways, of course. It backs out coal, but it also makes solar less attractive. And if, as we argue, what matters is not getting a little bit more of today's solar technologies deployed, but rather focusing on getting technologies for tomorrow, that's not a crippling problem if you focus on getting the long-run costs down. Yeah, continued deployment subsidies, yeah, continued deployment because it maintains a manufacturing infrastructure, focuses on some of the barriers I didn't talk about, like the need to have separate permitting activities in every city, town, and village in the United States, as opposed to a nationwide common policy in Germany. You can still work on those things with today's technology. But the fact that it's more expensive to deploy doesn't bother me much, because I don't really care about doubling the use of today's technology. I care about getting to 50 times solar generation using better technology.
So you were talking about the transmission costs, the cost of the wires with solar. But if we're generating the power locally, wouldn't the cost of transmission go down dramatically?
Okay, there are two issues, and maybe three issues. One, you're generating it, particularly for residential solar, you're generating it near households, but you're generating it typically at times when residential load is low. So when you have neighborhoods in Germany with high penetration of residential rooftop solar, they are pumping a lot of electricity out into the grid. That requires modifying the distribution system to handle reverse power flows. You can do that, of course. It's not rocket science, but it's not free either. So you save some on long-haul transmission, maybe, depending on where things are, but you impose costs on the distribution system. You don't save costs. The second point is the wires are there. So, you know, the wires are there and have to be paid for unless you basically stiff the local utility. Somebody's put up X billion dollars to put the wires in place. So you got to cover the carrying cost of those X billion dollars, and it doesn't matter that you're generating, that's still there. So 2 points, it adds costs, and you have to cover the existing costs anyway. I'm not opposed to distributed generation, but I think you have to look at it clearly. It's more expensive than utility scale. It does impose costs. Not necessarily a bad thing, but it is what it is.
Just a related question. What about community solar programs rather than having individual residential rooftops?
Yeah, in terms of costs, that's sort of intermediate between large utility scale and small residential. And there are variations on that theme. To use the rooftop of a large warehouse, for instance, is cheaper than using the rooftop of a small house. There is scale in installation and all of that. Community scale economically can be more attractive, depending on where there's vacant land and so forth.
Excuse me, is there any way to tap into community experimentation? In other words, as part of research, just to see how this is working, that's working. In other words, basically, you have communities that would be willing to ante up, so to speak, to be part of any type of experimentation or analysis or studies?
Well, 2 points. First, I think there aren't that many mysteries as regards the technology and the cost, right? I mean, it's a very mature technology. we may learn something about the cost of, say, automated hillside installation or something like that. So I'm not that excited about the potential, but it does lead to an important point, which is exchanging local knowledge, given how decentralized this system is an important potential federal role, a convening role. I talked about the fact that Germany has one national permitting system for solar, and we have one for every city and town. You're beginning to see initiatives, I know Connecticut has done this importantly, and I think other places have too, to try to gather communities together and say, look, if we had a common system, this would lower everybody's costs. If we had common rules, and the federal government can, I think, play a convening role there, because there are lots of sort of non-economic soft barriers that can be reduced. And that's one reason why I think it's important to continue deploying solar generation, because that puts pressure on those barriers, makes a convening role for the federal government valuable, and enables communities to share experience. I may be wrong. There may be brilliant innovations in community solar that have been done and nobody knows about. So I think sharing information, sharing best practice, trying to make permitting and related systems more uniform can add considerable value in the short run and in the long run,
So one last question.
Good morning. On your comments on DOE, I hear recently they're going to focus on stability of the solar panels, which seems would have a big effect on cost of electricity. Can you comment on that? That seems to have some wisdom and maybe a breakthrough in costs.
Maybe. I think the current technology, and people in this room know more than I, the current panels are pretty stable. I mean, if you can extend their lifetime a bit, it lowers the cost.
Yeah, they're focusing on 20 years going to 40 years. That would be a big deal.
That would be a reasonably big deal. Wouldn't cut the cost in half. Remember, it's just the module cost. And the module cost is a relatively small fraction of total cost, particularly at residential scale. I guess that's all fine. That's all fine. I think I'm relying on the judgment of my technical colleagues that there are more promising areas to work on. And I'll stop there.
I suspect you'll also hear later on discussion of stability issues in some of the emerging technologies.
Where they're
In some of
serious.
the novel emerging thin film, stability is a serious problem. And overcoming that is key to enabling adoption of those. So I'd like to thank Maria and Dick once again for very interesting comments and presentations, and like to invite the next panel to come up to the table. That'll be led by Dr. Francis O'Sullivan. Frank is Director of Research at MITE, and I'd also like to acknowledge that Frank is the guy that set this agenda up and did a terrific job putting this together. So thank you very much.
I hit the right point? You did. Good. Oh, sure. Happy to do that. Where do you want us here?
How do I advance the slides? How do I advance the slides?
He's got a clicker.
I got to click it?
Yeah. Thank you. Yeah, great. No, Tonio. You want to do that? Yeah. Perfect. Right in the middle.
Thank you very much, Bob, and Professor Zuber and Schmalensee for your opening remarks and the I guess that synthesis of the results from the Future of Solar study. I think it's fair to say that in the execution of that study, the complexities of the solar sector today were certainly highlighted, and I think it was also fair to say that we had a robust debate with regard to directions going forward surrounding many of the issues that ultimately boil down to economics. At the heart of the issue, of course, is ultimately the technology. And for the next few sessions, we're going to focus on the technologies, today's technologies, how they're evolving, potentially new technologies, with an opportunity to focus on the work here at MIT in that regard. And I think it's going to prove to be a very exciting and insightful couple of hours for everyone. We're extremely fortunate today to have some of our tremendous researchers, PIs here from the Institute, willing to speak about their diverse work with respect to photovoltaic technologies. On the panel here, I'm joined by Professor Vladimir Bulovic, who is Professor of Electrical Engineering and Associate Dean for Innovation in the School of Engineering, Professor Tonio Bonassisi, Mechanical Engineering, and Professor Mark Baldo from the Department of Electrical Engineering. We were also going to be joined by Professor Angela Belcher, but unfortunately a last-minute issue cropped up and Professor Belcher couldn't make it. The way the session is going to work is each of our panelists are going to make some prepared remarks with respect to their work and associated issues, and then following that we're going to have a discussion and we will open it up to some questions. So with that, I think I'd like to start and invite Tonio to the podium. Thank you, Tonio.
All right, thank you so much, Frank, all the organizers for pulling this together, and of course, all of you for your interest in solar. It's because of you that this is possible. I'm here to present the research at the MIT PV Lab. We live, breathe photovoltaics every day, and it's the core of our mission. This is a now somewhat outdated picture of our group from the 2014 IEEE Photovoltaic Specialist Conference in Denver, Colorado, but gives you a sense of the people who actually are responsible for the research I'll be presenting here. And several of them are in the audience and will be attending the poster session, so I encourage you to speak to the people who are really making things happen, not just the mouthpiece for the group here. What we consider to be a home run would be contributing to the development of a massively deployable photovoltaic technology that eventually has a potential to reach something on the order of 3 cents per kilowatt hour. Right? This is extremely aggressive considering today's technology where we're at today, but if we think about all of the additional costs needed to bring photovoltaics into the larger grid and ensure stability, some target on this order may be required. Right? And even if it isn't required, achieving it will have economic benefits beyond the simple deployment of solar, but also integration of solar into other areas that we might not even conceive of today. So a key point here is on the right-hand side, sustainable economics. We note that much of the economics that has driven solar development and deployment to date has not been sustainable in the long run, and we need technological innovation to get us to that point. So if we conduct a bottom-up cost model and translate this to a levelized cost of electricity, we can begin to define generic performance and techno-economic parameters that might define that future technology. We want to remain technology agnostic. We don't want to lock ourselves in too early in the process into one specific incarnation, but we do want to define certain techno-economic characteristics of that technology, and they are high efficiency. This reduces the area required to generate a certain amount of power, which has not only advantages in the material costs in the module level, but also in the deployment level in the system. Second is low materials cost that goes into the module. So if you can think of area being the efficiency leverage, materials cost would be the final dimension of the module through the thickness, through Z. Manufacturable, this relates to CapEx, we'll get to that in a minute, the cost of the factory. Bankable, this relates to the ability to raise funds to actually deploy the solar, which relates to the degradation rate, as one of the questions from the audience was. And fifth point is scalable. We need to ensure that we have the resources necessary to scale this technology up to the terawatt level. So if we look around and check the technologies today, what we have and what we don't, we find that crystalline silicon, which accounts for over 90% of the deployed solar today, is achieving several of these points here, but not certain critical ones. One is the material costs. The dollars per meter squared that goes into making crystalline silicon wafer cells and modules is a bit too high to achieve that long-scale deployment. And second, the CapEx is high as well. And if we look at some of the more successful thin film technologies, you have almost the exact opposite problem, where we have a streamlined or a more streamlined manufacturing process, the potential to reach something truly revolutionary, but currently lacking in the same areas that are the strengths of crystalline silicon. And so the R&D that is being developed, both in our laboratory and around the world, you can think of the individual projects as being puzzle pieces, right, that might fit into a larger technology of the future. Maybe one specific incarnation that I'm about to show you might not gain market traction, but the learnings from that may be incorporated into something in the future that does add up to this PV technology that'll drive us to the terawatt scale. So one route to high efficiencies that has been used extensively in so-called space solar, very expensive MOCVD grown 3.5 solar cell materials, but has really delayed reaching large-scale commercial deployment is tandem technology. The idea that if you combine two different materials, one on top of another, each of which absorb preferentially in different regions of the solar spectrum and reduce thermalization losses, you might be able to exceed the Shockley-Queisser limit of a single junction solar cell, thus enhancing cell efficiency. So just a brief overview of some of the activities there in our umbrella. We have activities, wonderful collaboration with CERIS, the Solar Energy Research Institute of Singapore. We grow the 3.5 materials. The silicon materials are being grown in a larger industrial collaboration together with CERIS. We're measuring the devices, and we're demonstrating to date, this is only about a year and a half since we've had the lab, 21.3% 3.5 and silicon tandem, an excellent learning platform to de-risk some of the technologies involved in tandems. We've translated some of those learnings into lower cost top cell materials. You'll hear a bit more about the perovskites, methylammonium halide perovskites, in a bit. But this is a potentially very low cost material, thin film, wider bandgap material that could complement silicon nicely. And some of the exciting results, perhaps coming from the bottom up in terms of efficiency, is if you are to combine a semi-transparent perovskite on the order of 12.7% with a very dirty silicon material, it's capable of achieving a 17.0% tandem, which is very interesting. This is in the range of commercial solar cells, right? So it's demonstrating the possibility of combining two potentially low-cost materials, a marriage of equals, and generating a tandem device that is capable of achieving a respectable commercial efficiency. So what can you do once you have these high-efficiency cells? You can begin exploring other integrations. How about coupling them with power electronics, with communications, and seeing what we can do as these component costs are being driven down by Moore's law? We can couple with storage. And we've done that successfully with a solar-to-fuel collaboration, in this case, with Dan Nocera, who's now at Harvard, by coupling the photovoltaic device directly to the electrochemical device without power electronics in the middle. Through good circuit design, you're able to achieve a stable operating efficiency of around 10% solar-to-fuel conversion with all earth-abundant compounds. And this was demonstrated last year in 2014 with silicon devices. So I'm digressing a bit from the main theme of solar modules, so allow me to return back there. I promised you that I would talk a bit about manufacturability. And I want to dwell on one term here, CapEx, which is short for capital expenditure or capital expense, if you prefer. And this is essentially the cost of the upfront factory, right? So this is what CapEx looks like. The reason CapEx is important is actually it's borne out in this photo, or this CAD rendering of the REC factory in Singapore. It's about a gigawatt fab, and all of this land in the background here is for expansion, future expansion, which never happened. Although REC is solvent, the expansion didn't occur because the economics are not sustainable for manufacturing or scaling the manufacturing without large injection of debt. And let me explain why that is. If your factory costs a lot of money, you have to put aside a lot of revenue to build your next factory sustainably, right? You can leverage it with debt and with other forms of investment, but in the end, you have to raise a minimal amount of capital to build your next factory. And that comes out of the margin on each product you sell. So what's shown here, oops, a little bit of a Mac to PC conversion, but what's shown here in these different colors is the operating margin of a modeled company using our bottom-up cost model. And the PP&E, this is plant, property, and equipment ratio to revenue. So the idea is you invest in equipment in year 0, you get revenue in year 1. And that ratio defines the capital intensity of your factory. These dashed lines, this vertical dashed line at 0.79 represents the wafer to module manufacturing chain, and 1.19 represents today's polysilicon to module, the entire value chain. The maximum sustainable growth rate, assuming a constant debt to equity ratio for our industry, even just wafer to module, is around 20%. And this pales in comparison to the observed 50% plus cumulative annual growth rate that was experienced between 2003 and 2013. Granted, margins were a little higher then, but not much, and certainly not enough to justify the massive growth. So as a result, you have an increase of the debt to equity ratio of certain companies. I notice certain companies because these were the ones that expanded, I would argue, beyond their means. There are some that were very disciplined in their expansion. You can see at the bottom there. And as a consequence, Yingli, which is one of the market leaders, is one of the 2 largest PV companies nowadays, is in risk of restructuring, shall we say. The position of number 1 has been coveted by PV manufacturers, but it's also high risk. About 5 or 6 out of the 15 companies that have occupied the first spot over the last 10 years are now no longer independently operating. Right, so it's almost a curse to be the number 1 manufacturer if you have an unsustainable technology. So how can we make it sustainable? How can we break down the CapEx? This is the CapEx broken down by process step within the silicon value chain. We notice that there's a lot of it right here, and there's a lot of innovation happening there, but it's happening within a fiercely low margin environment. So the ability to raise R&D money and critically capital to expand, CapEx, is lacking right now. So you see the pace of innovation happening much more slowly than it might naturally, but it's also a very Darwinian environment, and it ensures that the best technologies will survive. So one company with which we've been collaborating, called Crystal Solar, has attempted to take the traditional process flow and streamline it and say, why don't we take the silane or trichlorosilane gas initially and deposit a thin epitaxial wafer on a substrate that's reusable. And we could separate that wafer so that we have the silicon wafer at the end of the process, and then recycle the substrate. And cut down the number of steps, and critically the number of CapEx-intensive steps. Also, by improving the grams of silicon per watt, you're reducing the trichlorosilane CapEx. It's an interesting feature of the polysilicon supply chain. So through a lot of research, through our group, this is Mallory, I think she'll be presenting a poster today, holding up one of Crystal Solar's wafers at the company in California. Through a lot of defect control in the material, this was a tremendous amount of fundamental science work done, reaching now efficiencies that are indicative of monocrystalline silicon. Very exciting, 22.5% by the Crystal Solar team, together with the cell fabrication team in Japan, demonstrating a hit cell of 22.5%. And we inspire ourselves longer term. So these are steps we can take within the existing supply chain. Longer term, we like to envision a model of manufacturing that might be a bit different than today's disaggregated, disparate islands of automation with highly skilled labor in between, to a continuous process flow. And there are many industries that have taken that leap. Glass manufacturing, Gillette razors here in South Boston, plywood is a great example. And these are all industries that are heavily commoditized. Some are manufacturing in high real estate environments. And the goal is to produce a high quality product every single time without failure, and ensure it at low cost. So what is the equivalent in solar? If you look back in the literature, you find examples in the 1970s of roll-to-roll printing for solar PV technologies. This is a machine at University of Delaware at the Institute for Energy Conversion. And that was used to produce some of this material over here on the far left-hand side of this chart. These are the efficiencies of earth-abundant, scalable thin film technologies versus time, and you notice it's a very hard, slow slog to increase the efficiency traditionally. And what killed cuprous sulfide was the instability. We wanted a bankable material with a degradation rate of less than 0.25% per year, but in fact it was not bankable. The degradation rate was within days. The devices exhibited hysteresis and eventually failed critically. And interestingly, as history tends to repeat itself, there is a new material on the scene, methylammonium lead halide, or more generally, organic lead halide perovskites. And the really exciting thing about this is the efficiency skyrocketed from 2008 to current day, from around 2% to over 20%, asterisks, unstabilized, but it's a very high efficiency nonetheless. And this material is very promising in that it's low capex, but it's also unstable and tends to degrade within hundreds or thousands of hours, and by degradation on the order of 10%. And so the question is, can we discover, with our computational tools that we have at our disposal as a community, can we discover the next perovskite that might be more stable, might still retain some of the low capex advantages of the current methylammonium lead halide perovskites? We need better search criteria, and we need faster cycles of learning if we're going to do it. And I think our community right now is poised to tackle that challenge, and I think we can do it. We have the tools assembled, we have the right insights, it's time to go. So just in terms of search criteria, a lot has been learned from the band structure of these materials. Without boring you with the details, the nature of the electronic states comprising this specific band structure is, we believe, critically important to ensuring its defect tolerance and ensuring a high minority carrier lifetime. And we can predict the band structure and mine materials databases to find other compounds that exhibit similar band structures. We've done that, and 2 of the materials selected somewhat at random from a scientific point of view, intentionally from a manufacturing in our lab point of view, exhibited room temperature PL within the first 5 months of research. And this was a big jump forward from where we were before with some of those other earth-abundant PB compounds. So it's a very exciting time. You should expect to see some interesting work coming out from our community in this direction. And they might involve some elements that aren't the so-called traditional ones in solar cells. Big fluffy atoms, more in the poster session. So with that, I have 5 seconds left. I yield my time and welcome questions. Thank you.
Thank you, Tonio. I need to compliment you for your time discipline, Tonio. That was excellent. So before we go to Mark, I just wanted to ask one question. We'll follow up a little bit later. But right now, I think you provided a very interesting juxtaposition of where we are today versus path forward. What's the bridge? I mean, is the industry? Are there players out there who are looking to bring a somewhat newer paradigm to the market in the shorter term? Or, is there still a gulf between what we're doing today and what you kind of discussed there in terms of bringing dirty materials to the table and so on in moving that cost paradigm?
So I think one of the biggest challenges is innovating in an extremely low margin environment, right? So expecting industry to finance a $50 million consortium is rare.
Yeah.
We've been lucky in that regard, but fortunate, I would say. Luck plus capability. But I think moving forward, we're going to be looking at a much more critical definition of our value proposition. What are we doing differently? How are we adding value to the community? And we should be thinking about extending our work not only from the feedstock and the wafer up front, but all the way down to the system where you can capture a lot of value today.
All right. No, excellent. I think we're going to talk a lot about this throughout the day. Well, with that, I'd like to turn it over to you, Mark.
Good morning. My name's Mark Baldo. I'm here on behalf of a centre called the Centre for Exotonics, which looks at fundamental science in solar. And I wanted to give you our perspective on whether it's possible to do really radical changes in solar efficiency. So, I mean, what can we, should we assume that silicon efficiencies are basically the limit, Or can we really make major changes and really upend the way solar cells are built today? So to introduce this, and this is the work of a very large team here at MIT, I thought I'd just step back and say, all right, if we look at, say, a silicon solar cell, what limits the efficiency? So one way to look at it is, I have these different colors of light coming in. Let's say I've got some blue-green light, some red light that stretches out into the near-infrared out to sort of 1.1, and I've got light beyond that. All of this is coming from the sun. So right now, the silicon cell makes one electron from these photons, one electron from these photons, and it doesn't do anything with these. And what matters here is that all of the electrons that do come out all come out at the same voltage. So these photons that come in with roughly 3 volts, 3 electron volts of energy each, all come out with the same energy as the red ones, even though they're coming in with half the energy. So what could we do fundamentally to change this? Well, we're interested in something that we might be able to insert in the process in a solar cell, which is if we start with photons from the sun and we end up with charge, what can we do in the middle? So in some materials, just after we absorb the photon, we can make an excited state. So we can excite an electron, leave a positive charge behind, and generate a bound state, which is known as an exciton. So why would we want to do that? Why would we want to insert something in the traditional process of a solar cell? Well, what's interesting about these species is that they don't have a net charge. So they're the combination of an electron and a hole. They're neutral species. And that means we don't have to conserve charge. So we can cut them in half, we can combine them, and we can do interesting things that aren't possible in a regular solar cell. So let's look at see about that. So let's call this, if we're going to insert this this structure that's going to deal with excited states into the solar cell, what can we do? So we'd call this a so-called excitonic antenna, which actually borrows some jargon from photosynthesis, which is actually built off a similar motif. All right, so if we put a little coating that's going to insert itself in the process here, then it's possible, first of all, that we could take these blue and green photons and effectively split the energy. So instead of getting 1 electron for every one of these things, we could get 2. And that essentially doubles the return from this part of the spectrum. It's a little difficult to do anything with the red and the near-infrared because the silicon cell is actually quite efficient at harnessing those. But there's also some possibility here to take the near-infrared, which the silicon doesn't use at all, and combine those photons, those energy, and see if you can get 1 electron out where previously you got nothing. So this is quite a radically different design for a solar cell, and we thought, well, what's the fundamentals here? Is it feasible to build these kinds of structures? I should say, though, that before we talk about the work that we've done in this field, is that if you could do this, then the potential efficiency gain is very, very large. So it takes the silicon cell above 30. It's above 30 if you do this, and can even hit 40% if you can really do this part as well. And the last thing is, this structure is not in any way like a conventional multi-junction. So in some cells, Antonio introduced that idea, you would stack one cell on top of the other, and the current has to flow through both structures, which means they have to be matched. So if you have losses in one of them, it affects the other one as well. Here there's only one solar cell, and it's the silicon. So all the electronic piece of this problem is still done by silicon, which is quite good at it. So this thing can add, even if it doesn't work that well, it can still add a benefit to this overall structure, because essentially it's just pumping a little bit of extra energy into the silicon cell. All right, so let's look at the first part of the problem. Let's look at this blue and green issue. So if we want to take the blue and green light that has high energy, can we split it? So this process exists. We've done a lot of work here as part of the Center for Excitonics. As I mentioned, this is funded by the Basic Energy Sciences Office at DOE. And we've shown, first of all, that yes, this process is extremely efficient. It's essentially 100% efficient in some materials. So you can split excited states into 2. It occurs in a few femtoseconds. There's a lot of science here, which has been pioneered by my colleague Troy Van Voorhis in chemistry. And we've shown that it's very robust against disorder in these systems. So it's a very reliable process. And we've used it to generate prototype devices that produce more than 1 electron per photon in the visible part of the spectrum. So I'm just going to give a very, very brief overview here, but we can discuss this further afterwards. What about this process? So in the near IR, is it possible to take these excitons and combine them to get something that a silicon solar cell could harness? And so we've shown recently, and this is with my colleague Vladimir, who's on the panel, that it is possible to do this, that you can combine these excited states, pump them beyond 1 micron, and at intensities that are less than 1 sun, which is typically the problem for this kind of technology, and generate light which could be captured by a silicon cell. The efficiency of this process at the moment is a lot lower than the reverse process of fission, but we feel like this was a breakthrough since this is the first time it had been done in solid state at less than 1 sun. And lastly, is it possible to tie all this together with silicon? So what we're really looking for here is an interesting structure where we're doing essentially new science in a coating on the silicon cell using all kinds of new types of materials, but we need to couple them to silicon. And so it turns out that the issue is you need to get the energy to tunnel from this coating into silicon, which was a sort of unknown process whether that would work. And so we had a breakthrough last year again with my colleague Vladimir and Munji Bawendi and also Troy Van Voorhees' group in chemistry, where we showed it was possible to do this tunneling, and we saw it occur at 100% efficiency into quantum dots. Oops. And now we broadened that within the Center to look at the silicon problem directly, and we also looked at germanium as a proof of principle with the Kimmerling group. And again, we can see this occurring very efficiently. So my point, I guess, I was going to step back. This sort of concludes the technical thing I wanted to say, is that we strongly believe that solar shouldn't be viewed as although silicon cells are in a sense a mature technology, there's a large room for improvement in solar photovoltaic performance. And it's possible through fundamental work to imagine significant enhancements in these kinds of devices with very significant technical innovations in all parts of the cell. So this is one, and this is, as you can see, this work has all been done over the last couple of years. It's moved quite quickly. But we think it's quite exciting to imagine the new kinds of things that might be possible. It could push efficiencies in silicon up above 40. And of course, the reason, that's not just interesting from the module cost, but it is still probably the best way to get the installation down as well, since you need less cells to cover a certain area. All right, so that concludes what I wanted to say. I guess we could pick it up at the panel.
Yeah,
So.
well, that was great, to be honest. Just on this, Mark, I mean, today, clearly there's been work on multi-junction cells for quite a while, and that's a extremely expensive approach to take to move the efficiency limits. I mean, where are we? In terms of a science paper, this is all very exciting.
Right.
But how far away from, we can do this on a cell and perhaps even integrate it into a module, and it might actually be stable for a few years? How far away are you from that place?
Well, first of all, we need to be careful about multi-junctions. I mean, there's different kinds. So there's the lattice match type where you have to put every atom in its place and grow the thing very carefully. And so those kind of 3-5 materials typically. And there's a lot of work at MIT trying to reduce the cost of that by people like Gene Fitzgerald. Traditionally, though, that's true. Those have been expensive. The kind of perovskite multi-junctions that Tonio showed are not necessarily expensive. It's complicated. But yes, we would imagine this would be a very low-cost coating because it doesn't require atomic bonding to the... every atom doesn't have to be on top of a silicon atom as you grow this structure. In fact, we have an insulating layer that's glassy between the silicon cell and the rest. Where are we in terms of making something that's going to be commercial? Well, I mean, this is fundamental work, so we're still some distance. But I think the major issues that people in solar like to talk about, first of all, is stability. Mm-hmm. I think it's important to, and I say this, and I know Vladimir has a lot of experience in this as well, to understand stability is not necessarily an intrinsic property of the material. So even with the perovskites right now, they've been unstable. But stability is at least 50% a packaging issue. Right. So a lot of these new materials are porous. Perovskites are very porous, meaning that water and oxygen can get into them. And so we learnt a lot about this as a field in the commercialization of organic LED displays, which have been successfully commercialized and are in displays now. Cell phones and so on, and the packaging was crucial. So silicon has a nice intrinsic package, right? It has the oxide that grows on top of it, but with some of these other new materials, we have to build that piece, and that has to be done at cost. My view is that that's largely not a problem that's easy to work on in academia.
Right.
You can do initial characterization, you will probably determine that there's some issues, but with a lot of these materials, if you look at them intrinsically, it's not like carbon-carbon bonds are weak. There's plenty of examples of, if you were going to take that particular material, like molecular materials, there's plenty of examples of molecular paints that are used in cars and car paints and so on. So it can be stable, but it needs a lot of testing and investment. Our goal here is to demonstrate that couple this to a silicon cell and then see, hopefully, what industry will do with it.
All right.
Yeah.
Well, thank you so much. Vladimir?
Vladimir was being innovative with the instructions to send the slides beforehand.
Pardon me.
Yeah, that's all right.
No, I want to show a couple of videos, and I felt that Mac to PC conversion doesn't always do it justice. So I'll do my best here to give you a perspective on what could be done with different ways of thinking about solar technologies. I guess what you had a chance to see is tremendous advancements that indeed silicon has done, and then the opportunities, yes, of course. The opportunities that Tonio indeed presented that show you a variety of ways of thinking about how to enhance today's silicon, and then also how to think about the tandems, and then also how to drive the cost further down from where it has been to generate even less expensive modules that should then at the end yield, hopefully one day, 3 cents a kilowatt hour solar electricity. That would be entirely a game changer. You have seen Mark's opportunities in looking at new ways of using novel materials. And the result of that, indeed, would be to say, well, this can be a game changer from perspective of thinking how much solar spectrum would we be able to capture. And then the next question to ask would be, well, how quickly, how soon, and where are we going to see these new evolutions of solar technology? There is obvious way to see solar in the form that we have always used it, which is large panels that will be installed on the top of a roof or in a field and indeed provide a lot of solar electricity. A good question to ask is, how long did it take to get there? And if you look at the silicon technology, it's about 50 years or thereabout, maybe 60, that from the first time we've seen a silicon PV to where it is now. It took about 30 years to come up with the first uses, primarily in niche applications in space in the 1980s. And that was a fantastic advancement for the proof of technology, just like the use of a computer on an Apollo mission was the proof that computers can be useful as well. MIT had a hand in that. So if you actually look at what's next, you can say, well, it took a while for silicon. How quickly can we really scale up the uses of these new material sets that we are proposing? And indeed, if you look at even the simplest types of demonstrations of new hardware technology being introduced, for example, a zipper that took about 12 years from the first patents to first commercialization of a million people using it, or Velcro took about 13 years, organic LEDs that Mark mentioned, that took about 25 years from first demonstrations to the million people using them. Novel technologies that we're introducing do take patience and do take time to scale up, but they are born in the first idea that is transformational and indeed will revolutionize the future, not of tomorrow, but a future of a decade from now. I think we need to keep that in mind whenever we think about and see the next technology, because indeed the stuff we are using tomorrow has been invented a decade ago, if it's brand new to us. That being said, silicon technology led the way of the push of the solar deployment around the world, and we have consistently under-expected deployment of solar technology. These are predictions from year to year to year where solar will be. We are at about 200 gigawatts now, and we have, again, beaten what has been the prediction to where we should be by the International Energy Agencies that make their choices about how they evaluate conservatively where we should be next. The other thing that is remarkable is in the last 6 years, we have seen a drop of the module price of 85%. that's fantastic from perspective of the cost of solar. Notice, though, that the total cost of solar is beyond the module also the installation or the balance of systems that comes along with it. And that hasn't really changed very much over the last 6 years. Indeed, halving the cost of the module would maybe affect the cost of the solar installation in a large field only by about 1/6 of the total cost if we don't do anything about balance of systems. And so rethinking how to deploy solar is another opportune place to be to indeed affect the cost of the overall solar deployment. I'll show you these opportunities in the form of, again, novel technologies. Again, bear in mind, these are the things that we can show you today, have been invented a couple of years ago, and will be real maybe in a decade from now if they prove themselves commercially and economically. Compare the thickness of a typical wafer to a thickness of a typical thin film solar PV, and you'll find a dramatic difference. It has to do a lot with the physics of materials, the indirect band gap of silicon versus direct band gap of some of these new nanostructure material sets or thin film sets. And the emerging thin films promise to be even thinner because they happen to be optimized for the high absorption constants. We chose them because they're really good in dealing with light. That being said, the opportunities then stand at lightweightedness, modularity, and possibly integration of these ultra-thin type structures with already built materials, as a result allowing us to reduce the deployment costs, because you need to build whatever you're building anyhow, and it happens to have a solar cell integrated with it. The other thing to compare would be to look at the, indeed, how do you look at the comparison of these novel material sets to what has already been done and proven in silicon? And one way to look at it is look at complexity of material sets. Silicon is built of individual atoms, very simple material set, but to assemble it in a perfect crystal and indeed form it into a module, that might involve a multitude of steps of growing the silicon and then from there on being able to indeed form it in a format that could lead to a cell. The way that has been approached through the novel materials indeed to make a fairly complex looking structures. Quantum dots are very complex looking indeed item that you need to make many, many of, but you make it in a beaker. And in the case, for example, of molecular films, you make it, again, in a beaker, and then you can purify it prior to ever using it. So complexity of materials is very high, but the actual deposition methods through spin casting or simple evaporation of amorphous films that choose to make polycrystalline domains indeed has been a different way of thinking of how to form an active surface from which solar could be made. One thing we do need to keep in mind is in these new complex material sets, do ask yourself how many synthetic steps will it take you to get there. If it takes more than about 6 synthetic steps, it's too expensive. And the reason why we can say that so confidently is simply by looking at medical industry. Like whenever you, at pharmaceuticals, whenever you make complex molecules for pharmaceuticals, there is simply a cost that is pretty much related to the number of synthetic steps you choose to take in a big batch reactor. So in a big batch production of these complex nanomaterials, limit yourself to about 6 steps, and you'll be able to reach the very low cost per kilowatt hour. The other thing then to ask is to ask, well, what material sets, when it comes to the novel materials, should we really be focusing on? Carbon clearly is one of them, because carbon is just abundant as you wish. Another way to look at it is to look at the abundance of material sets that we choose right now for commercial thin film PVs. Compare it to silicon, and you'll find that for silicon, if we mine silicon for about 6 years continuously and applied all of that silicon towards making of solar cells, we will make enough solar cells to run the planet with solar electricity. Now, there is issue of batteries and so forth, but we're going to leave that aside. If I go ahead and say, well, how about cadmium telluride? Well, tellurium is not particularly available. It comes as a byproduct of other mining, and it would take about 1,400 years of today's ways of producing tellurium to indeed produce enough tellurium to make cadmium telluride cells to run the planet with solar electricity. Not particularly best choice. And indeed, if you look at much of today's commercial thin film PVs, they suffered a similar issue of it will take a long time to harvest the material sets needed to deploy them on large enough scales. But these new material sets that indeed have been emerging through perovskite uses and a variety of other things, for example, lead sulfide quantum dots have recently been used to make solar cells. It doesn't take too many weeks of mining lead and too many days of mining or hours of mining sulfur to indeed produce enough lead and sulfur to make enough lead sulfide quantum dots to make solar cells that run the planet. Now, that's the mining step. I didn't tell you about synthesis and deposition steps, which we really haven't yet developed or indeed scaled up. How good can these cells be? There are many ways of looking at them. Indeed, if silicon ultimate efficiency might be on the order of 32% for single junction, you can't expect these new PV systems will reach those kinds of efficiencies. But what you can expect is you can say, well, I can degrade their performance in a number of ways: lower fill factor, lower short circuit current, lower operating circuit voltage than I would expect, and you can still get reasonable performances, 17% or more. Indeed, the latest results from perovskites show performances over 20% in a brand new technology that validate in many ways the opportunities that are given by the emergence of these new material sets. But with efficiency being the only metric, we said that's not necessarily enough. Because even if I can give you a more efficient module, if I don't come up with a way to deploy it more rapidly and reduce the balance of systems cost, I'm not going to be able to give you a cost-effective solar electricity. What makes it expensive to deploy solar? Well, maybe one metric we haven't really spent much time on thinking is weight. How heavy is the solar cell? A metric that you can push forward, you can say for a 300-watt module, it might weigh about 30 kilograms. So you might get about 10 watts per kilogram in a typical silicon module. The new types of solar cells I'll show you now, for example, if instead of using silicon we can use paper, where would we be? Well, we would not be at 10 watts a kilogram, we might be at 100 watts a kilogram. How efficient is my solar cell? Well, not particularly efficient. As a matter of fact, they might be about a factor of 2 or 3 less efficient than silicon, but they weigh about 100 times less per square meter. So result of it is you can get significant watts per kilogram gain, or what is known as specific power. Would you ever use such a technology? Well, this is a very simple demonstration from a few years back that Karen Gleason's groups and my group worked together. A piece of paper colored with organic dyes that indeed, when connected to electrodes, can power an electronic device. Not a particularly power-consuming electronic device, mind you. We're using a very low power clock here to demonstrate, but it is indeed an entirely new way of thinking what a solar cell can be. And through rethinking of the formation of the solar cell and uses of it, this is indeed using it as a piece of paper that you can print straight on top of. Well, you can't quite use this, do this with conventional cells today and still connect them, shine light on them, and expect them to work like this one does. Now, through this, you can recognize that there might be new modalities for deployment of solar. And why do I need that? Well, because this technology, without packaging, will not last 20 or 40 years. I cannot indeed promise to you that this is a stable technology, but it's a fine technology to allow me to make new markets that solar can penetrate and new markets that can teach me how to stabilize performance over the next decade. So in decades' time, I can make impact into indeed making useful things that can cover large areas and be deployed for many years in transformative fashion. You can bend these many times and not find any change in their performance. Will they decay depending on material set you happen to use? But manufacturing paradigm now can be very different, high throughput through the abundance of materials, yet the challenge still is these low efficiency, low stability, and unproven ability to scale it, and giving us the guidelines for what we need to do over the next decade to indeed make them real. Nevertheless, these are the opportunities. These are the places now you might be able to find solar power. Or I often look at this image that shows a village somewhere in Africa with a solar panel and ask, how did that solar panel get to that village? Well, it likely happened this way, on someone's back, right? And indeed, if you ask NGOs, they'll tell you the last 9 miles cost a lot in the final cost of delivery of such solar application in a remote place. How many remote places like there are there? Well, there are about 1.5 billion people without access to grid electricity. And more likely than not, this is how they get their solar power. To that individual, efficiency of the solar cell is not as important as simply a metric of watts per kilogram. How many times will I have to make a trip back and forth to power my village? That is how much I can carry. The ability to indeed reduce the amount of weight might be done like this. And if you try making a solar factory that looks something like this, you can dramatically, again, reduce the footprint of a solar factory. Tonio has done some very powerful calculations saying that you can scale from, 2,000 square kilometers for a terawatt scale factory of using conventional way of production to maybe 0.01 square kilometer. the area of footprint of a solar production factory to generate a similar kind of production. Now, the latest developments that we looked at is indeed if this is the paradigm of how you can deploy solar, the plastics that you might use as a lightweight substrate, if one cannot sustain high temperatures, so you need to have low temperature processes, and secondly, they would be quite susceptible to electrostatic charging as they are being passed through the rollers, hence collecting dust, and dust is very big. This is a dust particles you might find on a typical plastic substrate. And then compared it to the thickness of your cell, you'll find the dust particles that accidentally collected will be just about as big as your cell. Maybe what you should do is actually make a system that makes your plastic substrate, and in the same system, make your solar cell. So start with a conveyor belt, make the substrate, deposit organic films, and encapsulate the thing, and peel it off at the end. This is a so-called Parylene technology that has recently been developed in our group by Joel Jean and Annie Wang. And indeed, they make these thin membranes, a few microns thick, as thin as a micron, let's say, and peel them off. And that is your place where you're going to put your solar cell. They're more transparent than conventional substrates. That's fine. But what is really powerful about them is the fact that you can make cells so light. Here is and so thin. This is a 2-micron type structure. Here it is sitting on top of a soap bubble. It's micrograms. But in the point of it is in order to be able to make a structure like that, you're really going this. You're comparing the thickness of that substrate to the thickness of a typical substrate. Will be comparing a piece of paper to the size of a skyscraper. And indeed reducing the watts per gram, the grams per watt of a substrate to dramatically low numbers. Now this 2-micron substrate will be ripped by you putting your finger through it. So the only other way to stabilize it would be indeed to apply it onto a substrate of its own. What would that be? Well, maybe a piece of cloth. My shirt doesn't rip very easily. It's about 150 grams per watt that indeed would be able to, 150 watts per gram, pardon me, that you'll be able to generate out of a typical cloth as a substrate. So where else would you see these kinds of new technologies? Maybe the first places is just to ask very simple consumer electronics type uses. This is a quantum dot PVs on top of a piece of glass. You can use it as the coolest pair of sunglasses, if that's what you want to do. Why would you care about that? Well, you might need power to power a hearing aid. Indeed, the amount of power generated from this particular structure is sufficient to power a hearing aid. It actually is even sufficient to power a Bluetooth radio if you have a high-efficiency Bluetooth radio. And then you can imagine other types of technology, again, using these nanostructure material sets. This is a transparent solar cell that looks like a piece of glass. It's 95% transparent, because we've chosen nanostructure materials that do not absorb visible light, but absorb only infrared and UV light. They don't generate as much power as silicon cells, but they do generate enough power, again, to run common electronic appliances. Here is one of those cells mounted on top of a Kindle reader. Why? Because it doesn't use very much power. And here it demonstrates the transparency of the cell. Anytime you uncover it, you generate about 10 volts coming out of that structure under room light. And anytime you cover it back, again, you're not getting much energy. But you have been all throughout this particular video looking through the cell to see the screen, because this is the cell that indeed is generating that power, allowing you to reimagine what electronics can be. Indeed, this Kindle doesn't ever have to be recharged again. In a course of everyday use, you'll get enough solar or light power to indeed power it. And as a stepping stone of learning how to make it bigger so that one day you can truly affect what truly matters, which is the energy footprint of the spaces we typically utilize. So I will stop at that point and leave you with a note that I think rethinking what solar can be is a dramatically important thing to consider. The formats of today's deployment are geared towards the developing world that's spending most of the energy of the world, and indeed is geared towards large panels of fixed format. The things to consider would be to ask what would be opening up by choosing to use less efficient cells, because simply new technologies would be needed, but ones that are extremely light and hence easily integratable in our everyday environments. Thank you.
Vladimir, thank you. Thanks, Vladimir. That was great. Actually, a really interesting statistic. So you said a contemporary panel, let's say 300 watts, about 30 kilograms. You know, that's only twice as powerful as a decent human athlete. for an hour. It's kind of, it just popped, that was a very interesting statistic.
So it turns out those Parylene solar cells are about 6 watts per gram.
Yeah.
Not per kilogram, but per gram. 6,000 watts per kilogram.
Yeah, I think that's really quite a stunning example of the opportunity space, perhaps, that we have ahead of us in thinking about solar and how we deploy it. Tony, I'd just like to come back to you to start the discussion period here. So, based on your numbers, 3 cents per kilowatt hour ballpark is a target.
Right.
So today, I mean, there are PPAs being signed for 6 cents per kilowatt hour, and there's 20 or 30% of subsidy thrown on top of that. So we're certainly let's say 9 cents per kilowatt hour. So that doesn't feel that far away, yet it's still a long, long way away. How do we, in the shorter term, how are we going to be able to take what we're doing and move, and when I say short term, the next 10, 15 years, the type of timescale that Vladimir is saying will be required in order to develop these new paradigms. How are we going to move today's technology forward? Because certainly, as Professor Schmalensee highlighted, the reduction in price of modules and cost of modules has certainly arrested recently, and now we're thinking about the balance of system and so on. Have we any runway left have we enough runway left with contemporary silicon?
So let me preface this by saying that we look at the sustainable growth of solar. If you want terawatts,
Right.
Some of the market fluctuations that lead companies to bid at 5 cents per kilowatt hour in Austin or Nevada may not persist.
Right.
So that's a whole nother discussion that we can get
Absolutely.
into in the break. But on the technology side, there's still a tremendous leverage of efficiency on the system, right? So if you improve the efficiency of your module, it requires less area to produce the same amount of power, and that affects all the material costs that go into the module. And then on the system side, it affects the racking, the framing, the labor, right? And a whole slew of costs outside of architectural fees, insurance, and inverters, things that are area independent. And so there's a very large lever of efficiency. The second big lever is reliability, right? Because if you're doing an LCOE calculation, it's true that when you factor everything into the NPV, the net present value calculation, what you produce in the near term matters a lot more than what you're producing out in 20 or 40 years. But still, if you can get that extra runway, it does have an impact on the LCOE. So from my point of view, the module itself is still a linchpin of the system. And it's something that increasingly has to be looked at as part of a system, not just an isolated area of research, but integrated in with the system. If you look at the maturest markets, not the ones that, as Professor Schmalensee was mentioning, are a little bit distorted right now, like the residential. But if you look at the maturest markets where you have the greatest insight into the economics, large-scale deployment of solar, the module is still comprising around 45% of system cost, right? So it's not a negligible cost. So I would argue that there's a lot to be done up and down the entire value chain, but let's be fair and look at the sustainable deployment of solar rather than try to base our R&D plan off of maybe what might be a short-term perturbation or trend. Just to give you one example, the ITC cliff coming up, there's a lot of incentive for installers to have projects on their books. And so there's a little bit of a mentality of bid now, figure it out later, right? And if they can't make a bid work in 2022 when it's expected, well, then they just back out and the thing goes up for rebidding. Nevertheless, that number of 5 cents per kilowatt hour is what sticks in everybody's minds.
So, I mean, I think that's a very important and salient point. Ultimately, it's the tech, it's the module and what you can do. And I think, Mark, in terms of what you were displaying, there seems to be great potential to do a lot more, even with today's silicon modules, let alone going to, to entirely different paradigms. But at the same time, I think there's a challenge now in terms of our R&D policies and so on, in terms of where the focus is on. Should we, and I'm asking the three of you now as principal investigators in this space, where do we need to be really focusing our R&D efforts on in order to kind of help realize this solar future?
I'll be brief. I think right now the mission statement of solar has broadened.
All right.
When it was 20 years ago, and solar was way too expensive for any large-scale deployment consideration, it was very easy to pick one narrow segment of the value chain and say, I'm going to work here in this little niche. Now that we're seeing the beginning, the approach of the inflection point, we suddenly have to consider the integration, the interconnection between what we're doing and all these other aspects, all the way down to the end customer. And what's really needed is a composure, right? We need to step back, look at the fundamentals, and think critically, based on our models, what do we really need to affect for this larger system to move forward without locking us in too early into one particular path, right? What could have the biggest possible impact downstream? There is still a lot of potential for innovation. And just because we're in a margin-constrained environment in a high CapEx manufacturing world does not mean that we should be pushing all the innovation off the table.
Mm-hmm.
It just means that we need to be more critical and thoughtful about the return on investment.
Mark?
I guess, so I don't have a lot of expertise, I guess, but obviously we need a balance between the near-term optimization of our current technologies and looking at some further afield, because there is potential for significant changes in performance. I guess the one thing I would say that would be interesting for people on the policy side to consider is one of the key issues in the middle of this is stability. And it's typically a set of problems that aren't handled well in our current sort of R&D environment, because it falls somewhere between academia and industry. It's hard for academics to work on it because it's not good problems for grad students having thousands of cells under test, and we're just not set up for that kind of boring work. But without that data, you can't actually move the problem ahead. And in industry, they're not actually well set up to handle the key problems in the science of stability. And so I agree that stability is a key issue. And it could be completely decisive in some of these new technologies like the perovskites, where if they can't solve the stability, they're going to die. But at the moment, there's no clear plan on how we're going to solve this, I think. At least it's not as organized as well as it could be. And so I think that's something that we might want to consider going forward.
Yeah, I think Antonio and Mark open a set of large challenges, call it, ahead of us in thinking about it. And I think it reflects, I'm going to just step one step further back and emphasize the fact that just the way our innovation economy operates has changed. And this is, I think, at the detriment of our present opportunity to indeed advance technology as rapidly as we used to. And very simplistically, that large corporations that do innovation are not really connected as well towards innovation places like universities. And also the middle years of innovation have pulled away from truly doing radical applications of new discoveries towards perfecting already existing technologies just a little bit. So big companies are working on just perfecting things. Young places like universities are inventing 1,000 crazy ideas with no rooting in the feasibility necessarily of the scale-up.
Yep.
And the middle part is left to startups to think about how to indeed bridge the gap. And the fact that startup as the vehicle for launching a new idea that's meant to bridge to the industry and address the final industry need, that is not necessarily a sure thing. And hence, some of the industry need, what needs to be happening, right, is pull back towards that innovation stage, except the profitability of the solar companies is not there to allow the investment in this R&D corporate lab research kind of experience. So I think we have a big conundrum between who's going to do that translation bit.
Right.
As universities, we are coming up with a lot of things that really don't matter, and then some that do matter. And those that are really cool looking, like these lightweight cells of ours, you can say you can launch as entirely new technology that one day maybe will offset what industry is doing right now. But it really doesn't solve the issues of what industry needs right now, which is that translation stage from the basic idea that Tonios works on towards actually someone testing it out at scale and then someone adapting it towards being able to truly use it. So I do believe there is a tremendous amount of innovation that's on the table right now that we are not exploiting to the best of our ability due to the innovation system in which we live.
So, I mean, this is a common narrative for energy technologies, right? There's that challenge with scale. I guess I have two questions. So I guess the first question is, we've had this, so if you take the silicon paradigm that we've had for a long, long time, and you start out with, growing CZ crystals, and you run it all the way through to, your gigawatt factory, that's just an impossibly large kind of capital demand. And it's, you know, you make a bet there and you got to run with it for a long, long time. What you guys have been describing today, I would characterize as certainly technologies that perhaps are more amenable to less capital intensive on a specific basis technologies. Still certainly going to be capital intensive, but how do, I mean, are there are there support structures that you can think of that would allow us to kind of exploit this innovation where we're taking kind of CapEx out a little bit, at the same time bridge to actual deployment?
So this is, I think, to a large degree, where manufacturing meets materials.
Right.
Right. So I think this is symptomatic of the maturization of solar. We're not yet in adulthood. We're in adolescence somewhere, and it's tricky. But we need to be able to weave in many more disciplines to make solar successful. And one of the disciplines we really need to weave in a major way is manufacturing. Right? Vladimir alluded to this when he was counting particulates on the plastic.
Yeah.
That's really important. Mark alluded to it when he was leveraging existing technology to launch a new addition. And I think the whole CapEx question comes back to it. How do we accelerate the rate of equipment design, right? So that we take a lot of the time and money out of the development of new tools. How do we develop smaller tools with higher throughput? I think that's really the key to reducing CapEx is throughput without sacrificing quality. And quality is both performance and reliability. So these are some of the key questions that need to be addressed on the manufacturing side. And it can be tackled through a variety of software, hardware, but also financial engineering approaches. If you could move to a leasing model instead of an outright purchase model, that would move a fixed cost into a variable cost, at least for the manufacturer, not for the equipment build. And that would require a rethink of how we manufacture our equipment, perhaps disassembling it into Lego blocks that can be reassembled into other things and repurposed later, so we retain value in the components.
So I would add to that from perspective of nanostructure materials, there is one saving opportunity, which is indeed the uses of nanostructure materials are just emerging on a stage as being viable in a variety of technologies, and one that is very big now is organic LED technology. And it turns out the Achilles heel of organic LEDs is manufacturing. So there has been over the last 15 years tremendous amount of investment in developing tool sets to put down nanostructure materials over very large areas for the sake of making displays, not solar cells. But those very same tools could be loaded with different nanostructure materials that indeed could produce solar active structures of high precision, high quality, no defect tolerance. I mean, simply no defects, because when you make TVs, you cannot have bad pixels. Actually, when you make solar cells, you can have bad solar cells. No one will know, right? And that's okay, right? Because you still get the performance on average that you expect. So adapting some of the tools that have been done more recently for the production of organic LEDs will essentially offset the cost of CapEx and simply straightforward adoption into this new nanomaterial space. I wonder if there are similar comparisons, and there are some. I mean, Applied Materials, for example, has utilized their capability to make large semi-tools and then to apply them towards the production of the PVs. Those kinds of correlations of industries, I think, are one way to push forward the advancement of PVs.
Remind me never to buy a solar cell from you then, Vladimir. That's your manufacturing attitude. No, actually, so being dead serious though, I think on this, so Tony, you mentioned something that I thought was quite interesting, the kind of so-called dirty materials paradigm, right? So can we move to, are we, is that technology frontier that we're going to be following down involving a set of materials that are going to be, easier to work with?
So this comes back to material science and the strong role of materials and chemistry in materials design. So if you want to broadly classify PV materials today, there are about 3 classes of them, right? There's the covalently bonded semiconductors, which are exquisitely sensitive to parts per trillion concentrations of impurities, like silicon, right? And to some degree, gallium arsenide. On the other extreme, we have materials that are, for whatever reason, inherently robust against defects. And you can add impurities into methylammonium lead halide materials and still get 12, 15% solar cell. In the middle, there are a number of materials that are more ionic in character, like cadmium telluride. They're not so ionic that they become rock salt, but they're still in that traditional diamond cubic-like structure motif. And these require more pure, not tremendously pure, but to give you an idea, First Solar has purchased a large part of 5N as its feedstock company, which gives you a sense of the purity levels required for some of these thin film materials, right? So it's an intermediate purity level, which again stems from the more ionic character of the bonds, which renders it more defect tolerant, but you still can't, you can't snooze on the job. You can't put in parts per 100 of impurities into these levels. And unfortunately, in academia, many of our feedstocks that we work with in the lab are parts per 100 or parts per 1,000 pure. Right? So it's this white elephant in the room that we're not really addressing, which is the impurity levels inside of our materials, just because it's an extremely hard problem to tackle, to identify, characterize, and remediate.
Oh, that's very good. Okay, so at this stage, I'd like to open it up to the audience for some questions. And this time, I would like everybody to identify themselves and who they are and where they're from before they ask the question.
Okay, Janice Marconi, and Stonington, Connecticut, Marconi Works International. About 3 years ago at Consumer Electronics Show, I was talking to one of the researchers at Corning, and we were talking about flexible glass, and I guess now it's called willow glass. To anybody, but specifically Vladimir, but anybody else, it looks like it's up to 500 degrees Fahrenheit. It can be on a flexible roll up to 4,000 square feet. The laminate properties look fantastic. When I was talking to one of the researchers at that time 3 years ago, he says, this is so fantastic. We don't even know what all the applications are, but it sounds like it has the properties that you're talking about. Your comments, and I don't know if I'm sure you've heard of it.
Oh, yes. I do not know this for a fact, but I would expect that the form of a willow glass or equivalent of it is, for example, in Samsung Edge, the phone that has a bent screen that uses nanostructured organic films to make the screen itself, as an example.
It's not Gorilla Glass, it's the willow glass, so it goes beyond that.
The cost of the glass, indeed, any step you take to make the extra cost of making the substrate is extra cost in the scalability of your solar cells. The willow glass is not as cheap. Gorilla Glass is not as cheap as making conventional substrate. So it is not to say that that's a bad idea. I think it's a fantastic idea to utilize a glass as a substrate because it provides a perfect moisture, perfect oxygen barrier. At the end of the day, I would love to imagine a way to indeed make a cell that doesn't require that kind of stringency in the substrate. And that will give me a scalable technology that I will have to not worry about quite as much. Will it crack? Will it indeed let the degradation materials into my cell? So it's a good idea, and indeed it's a fantastic technology, but it's the very early stages of it being useful or scalable.
Maybe I could add something about that. Yeah, I want to just reinforce Vladimir's point about the Samsung Edge phone, because if you look at that thing, it's got the display is curved over 90 degrees in a very short bending radius, and it's quite a remarkable. It's a remarkable piece of engineering. It's unclear what the purpose of this really is, but from our point of view, it's showing that these kinds of flexible platforms can start to be built. Right. So I think traditionally there's only been two materials that have sufficient or lack of porosity that can be used to package these kinds of materials. One is glass and the other is steel. And so it's nice to see this start to appear in products, I think. I actually don't know what Corning product it is that they have used there, but the bending radius is very, very, very short.
There are technologies now that are being developed to indeed do the packaging. If you look at, for example, at that particular screen, the package behind the glass that protects the display is only 20 microns thick. And it's nanostructured materials followed by other nanostructured materials on top that indeed give the moisture, oxygen barrier seal. And it needs to be that thin because actually curvature would crack it otherwise. So you need to have extremely thin structures.
And I mentioned the difficulty of innovating in a capital-constrained, high capex, low-margin environment. Glass today in solar modules is on the order of $5 per meter squared. So that's the bar that other competitors have to reach, right? It's really the margins have been squeezed out of the glass manufacturing for solar, the traditional low iron anti-reflection coated glass.
Kate DeWolf, I'm a military contractor. I identify energy efficiency and renewable energy projects for military bases, right now for the Army at Fort Devens. So I'm interested in LED lighting and solar panels. So, you know, a PV technology takes in a photon and makes an electron, and LED lights take electrons and make photons. How linked are these technologies for the huge LED lighting industry?
How what? How?
How linked? How do they play? If there's a breakthrough in PV, is there a breakthrough in LED lighting?
Oh, well, so, I mean, both Mark and I had the experience of living through the innovation of organic LEDs as a technology, and only to find out that at the beginning of the 2000s, when OLEDs became efficient and companies took them on, all of the researchers had nothing else to do, so they decided, let's go and focus on PVs. And so you start seeing from the early 2000s tremendous advance in organic PVs because we finally actually started paying attention to another industry because we had nothing else to do. And so I think the two are linked. I think they're linked in the intellectual capital of individuals. I think the other way that they're linked is indeed in the CapEx discussion that Tonio pushed forward, which is to say that some of the tool sets developed for a very lucrative OLED industry can now be applied towards the manufacturability of the PV industry. And I think vice versa as well. I mean, we learned a lot, for example, from the photographic film industry when it came to that predated, right, the ability to make OLEDs, and that was kind of coincidental with the Xerox industry, which was another way of putting down micron-thick films of nanostructure materials that started in the 70s. So every one of these, indeed, has been building on the other one, with always pushing the envelope of performance of the previous one to make the next one.
I would add a healthy solar cell has a high quantum efficiency and radiative recombination. You will see a solar cell glow if it's happy. Right? It will be very weak, but you will see a glow, and our techniques can detect it. So there definitely is a correlation.
Hi, my name is Christoph Reinhardt. I'm from MIT Architecture, and thanks a lot. That session was a lot of fun for me, really great to see. I think one graph came up twice that really showed how much you guys have done your job reducing the cost of modules by 85%. And then in a way, when we look at it, it seems like the building industry has completely failed to reduce cost at all, like in the last 15 years. So I wonder what you think. Does that mean we should put more emphasis in research into or training into changing the building industry, the installers? You kind of stop at manufacturing, but I think the installers and the people that put it on the roof, do you think there's a lot of potential to save, and who should pay for that, and should MIT do anything in that realm?
I have strong opinions, but okay. I think absolutely MIT should do a lot about it. I think the other thing you should bear in mind is that when architects design buildings, those are meant to stand for 150 years before someone will choose to knock them down. Can I give you a technology that I can ensure will be that long? Maybe I can give you a film so that anytime you wash your windows, you can peel it off and peel another one on. That's a different way of thinking of technology, right, that you might choose to have deployable. The other thing to consider is to ask, well, what if your roof leaks, your roof made of solar panels? Well, you can't just hire the builder to come back and fix the roof because he might get electrocuted. You better have the electrician on site as well so he can make sure it's wired properly at the end. That's very expensive, right? So the benefit of actually making building integrated structures a priori from which you're going to build the building itself, you really have to make a good, careful choice. Is that the right choice for you for the long-term operation of the building? And so at the end of the day, the builders, as I understand them, are very, very careful about adapting anything particularly new. There was a tremendous, for example, recognition from the civil engineering department here to recognize that you can use cement, a different ratio with respect to make stronger concrete. And you can reduce CO2 emissions by choosing the right kind of ratio. But who's going to adapt that? I mean, if you choose to adopt a new technology, you're at the liability of building a building that might crumble, and you might go ahead and be sued for that and be. So the stakes are so high that we better have something extremely well proven before you can build it in. Light bulb, sure. You'll put in an LED light bulb without thinking twice because it's easy to replace. It doesn't cost you too much. So maybe modular buildings, that's maybe the way to think of it with this new technology. Can we give you modules you can just easily swap in and swap out so that you don't have too much risk adapting and trying us out?
So I'm going to...
Can I just a direct response to that? I wonder what you think, and I think maybe generally. See, a roof has to be replaced in this country ridiculously every 15 years because we use these cheap asphalt panels. So, I mean, there you're in the same kind of order of magnitude.
That's a perfect use.
Thank you, Christoph. Your German side didn't just shine through there. So I'm going to ask a final question now. In the spirit of today, learning about what we're doing with respect to solar research here at MIT, I think my compliments to the three of you. It was fantastic. You really demonstrated some tremendously interesting work, important work. My question is, can we do better as an institute? We might be doing as good as we can at the moment, but if we can do a little bit better, what is it that we need to do here at MIT to have even greater impact and to kind of take the innovation, the student capacity that we have and so on, and to move these frontiers forward? Nobody?
I'll start, because Vladimir's probably going to give a good conclusion, I think. So I'm probably the least expert on that problem. I'd say, and Christoph raised this, that for many people in the technology area, like perhaps many people in the technology area, I have a weakness in my understanding of the building integrated problem. Right. And to the extent we think about it, it's been very difficult to know what should we be optimizing in that space. So basically we just say, all right, let's just make efficiency stronger because that's the biggest lever. And since we're working on something far out, our philosophy is, well, it better be a big change in efficiency, otherwise no one's going to bother. But it would be nice to know exactly what would be useful in the building integrated area, and that requires a lot of feedback with industry. The second thing is, I do think stability is a growing problem, and we need to change the way we think about it, I think, and start to look for interactions with industry to start to work on these problems, because there's important science problems in there, and we know that from the OLED space. And it will take a combination of us and industry to solve those issues. So I think there are two areas where we could grow a little bit, I think.
I'll continue upon that theme of bringing new insights into what has traditionally been a material science and electrical engineering heavy community. We do need to bring a broader group of folks in, including architecture, but especially manufacturing. Right? A lot of the issues that we'll face in scaling up this to the terawatt level, the linchpin is manufacturing, and we need to innovate in that area. The second thing that I think we can do as an institute is we have a tremendous reservoir of insight into the technology and into the fundamentals of the economics, not the market price fluctuations, that too, but really the underlying fundamentals. And we have the potential, nay, the responsibility to identify what technological levers need to be pulled to ensure that this technology can make it all the way to the terawatt scale. Right. We have a unique position and hence a unique responsibility to do this. And I think by continuing to push forward, even in a time when the economics might be pushing us the other way, saying, short-term pricing might be pushing us the other way, but the long-term economics are pointing in the direction of solar, requires us to have a little bit of a steel nerves at this point, right? As things fluctuate, as something might not be hot, but might still be important, right? So that is an additional consideration and a responsibility of our institute moving forward.
I guess I would conclude by saying that as any other university, but especially MIT, we can solve any problem, but we often don't know what we need to be working on. And as a result, insights from industry are extremely important. We don't really spend sufficient amount of time. The time is always precious, and we focus typically on fundamental discoveries, which are fantastic and needed, but why do they matter? What is it that the world will be accepting of it? We can only fathom that by kind of giving a glimpse of today's news, and we say, oh, the news magazines really tells us this is a really cool thing to have, I'll work on it. Yeah, there's cool science, that's really why I'm working on it, but this is why I'm doing it, for the sake of the world in that way. And I feel like, that question on buildings is a fantastic one, because there isn't, I don't think at MIT, sufficient amount of interaction between the School of Architecture and our random discoveries in the School of Engineering and School of Science, our random technologies. There is some, but by no means have we exploited that to the maximum, so we truly understand where can be the impact of these novel kinds of ways of thinking of what technology can do. In the same fashion, some of us are true experts in understanding where, for example, silicon technology is heading, because Tonio does spend a tremendous amount of time being truly immersed in industry, but not very many people have an ability to do that, or knowledge of how to do that. So another way of indeed learning is to bring industry to campus. Ask one expert from one company to spend not a day with us, but a year with us. Embed them inside this or that group that cares about the technology. And from there, be able to obtain from them a tremendous amount of knowledge of what truly industry wants. So we can become a little bit more useful and a little bit easier to translate what we do into the impact, and at the same time provide a pipeline for our students to be recognized by industry as the candidates to be hired to be able to change the world through the practical uses of the knowledge they gained here. I think the other thing would be kind of nice to have just around somewhere is on one of the rooftops, somewhere easily accessible, a solar testing facility would not be bad, right? I mean, we have them inside the labs. We have ways of simulating light and testing how well the cells work. But wouldn't it be cool if you can go up the steps and there's a little glass house and there is your cell working, or there you bring a class and you say, oh, look, this makes this much sunlight, here's the sunlight of today. Today is not particularly bright day. It'd be good to know how much less power am I making today than yesterday. Right. I mean, I can tell you the number, but it's very different from actually physically experiencing, or knowing that your friend George, made that cell and stuck it there yesterday, so you can go in the lab and make your cell and stick your cell up there as well. I mean, that's hands-on examples we have always excelled in. So one cool thing to think about would be to ask, are there spots around the campus? Have a little bit of a sunny roof, easy to access. We can make a little glass house up there, so in wintertime it doesn't get too cold, and we can go ahead and test some of the cells.
What about the
MIT
fab?
Nano.
Oh, yeah.
It'll cost you.
Thank you, Frank.
Well, with that, I would like to invite you all to thank Vladimir, Tonio, and Mark for the tremendous input. Thank you, guys. So we're going to take a brief break. We'll reconvene at 10:45 to discuss solar thermal. Thank you very much.